Hello, and welcome to an abbreviated overview of phylogeny. Before we get started, let's remind ourselves of how life works. We don't live forever. New individuals are born as others die. Over time, new generations of organisms replace old ones. By luck, and inconsistencies thanks to mutations, new variations might arise in some of these new individuals. If these variations are beneficial, they might take over a considerable part of the population, even outcompeting the original variant. Here, let's assume that different shapes and colors can't reproduce with each other. Speciation doesn't have to occur evenly. In the bottom left population here, only one new species has appeared, but in the top right, there were two. Perhaps the conditions up there drive faster evolution and things are more stable down here, or something. Also, a friendly reminder that species can go extinct at any time. That's the basic idea. Without getting into the details of how circles evolve into hexagons, let's have a look now at how evolution can be driven by dramatic new geographical features, and how it can proceed without them. Here's a nice wide-open plain with something living on it. Over thousands of years, a mountain range splits the population in two. Because conditions are drastically different on opposite sides, the smaller population on the right quickly evolves into another species. This is allopatric speciation. The original species might also change over time. Perhaps the members get larger. And now, given even more time, some in this bigger population might develop different living habits and branch off into their own species. The two coexist with each other, but can no longer breed. This is known as sympatric speciation. Seeing trees split is all well and good, but in the real world, we must reconstruct organisms' evolutionary history by looking at their characters. So let's do that. These columbines are flowers with 8 characters, each having 2 distinct character states. The stigma can be white or orange. The anthers can be white or yellow. The blades can be white or yellow. The petal tips can be round or pointy. The petals can be white or blue, stripes can be absent or present, the spurs can be short or long, and the spurs also can be white or blue. Let's say we have these 7 species to organize. One way to figure out the lineages is by making a data matrix. Let's fill it in. For this first species, the stigma is white, anthers are yellow, blades are white, petals are round and white, it has stripes, and the spurs are short and white. You get the idea. So you can either take my word or check yourself that the rest of the table looks like this. Now we go column by column and group the white backgrounds together and the red backgrounds together. Only 6 has an orange stigma, so it can go over to the right. 2, 5, and 7 have white anthers. Let's put them on the left so that the yellow anthers can make a group as well. 5 and 7 have yellow blades. We'll make a note of that. 3 and 4 have pointy petals, and only 3 has blue petals. 1 and 6 have stripes, 7 has long spurs, and 2, 5, and 7 all have blue spurs. Here's the simplest, or maximally parsimonious, tree that comes out. Each new branch is defined by some distinguishing character, and some monophyletic groups have multiple. This particular tree has no root since we didn't specify an outgroup. You could also do all this in your head and group flowers on the fly. For instance, if we try this again with some fresh flowers, 1, 2, 4, and 7 all have orange stigmas and round petals. 3, the only one with blue petals, shares long spurs with 6, so we can stick those together. And that's probably all the shuffling we have to do. Now we can be systematic about labeling characters. 1 has yellow anthers, 1 and 2 have yellow blades and blue spurs, 1, 2, and 4 have stripes. You get the idea. We can fill in the rest like this, and there's our tree. Practically painless. If you really love these flowers and just can't wait to try this out for yourself, here's another set. Go on. I'll wait. Okay, if you're ready, here's the answer right now. And if you're more than ready to move on, we can do that too. One way to test a tree's robustness is with the statistical method of bootstrapping. Let's try that out with this matrix of molecular data. There are 5 species, V, W, X, Y, and Z, and an outgroup, which I have here as omega. Here, each character is a specific site on the sequence, and for that site, different letters represent different character states. For instance, the character state of character 1 is A in 2 species, and C in 4. We can make a tree with this information as usual. The most parsimonious one looks like this. Of course, individual characters can give us different or even conflicting information. On top of that, the tree might accidentally indicate something that's not true. So what we can do here is separate each character while keeping the respective character states of each species intact. We make an empty matrix the same size as the original. And now we simply choose randomly from 1 to 10 until it's filled. Let's use the suicide prevention hotline. And I've just made things awkward. Notice how numbers can be chosen multiple times, or not at all. Not removing selected numbers as they're chosen, or sampling with replacement, ensures that each character has the same 1 in 10 chance of being selected each time. This particular matrix gives us this most parsimonious tree. It looks pretty similar to the first one. Let's try it again with the first 10 digits of pi. 3.141592653. And we make another tree. Yep, still the same thing. And we do this hundreds or thousands of times. Each tree has its own distinct bias, but on the whole, they should all cancel out as noise and leave only the signal. Here's the tree from the original matrix with bootstrapping values. These are written in percentages. This 80 means that this pairing occurred in 80% of the most parsimonious trees deduced from the randomly generated datasets. With higher numbers, we can be more confident that these groupings are valid and not accidents. Generally speaking, 75% and up is considered significant support for a group, and anything under 50% does not meet the threshold. If this bottom node were a 28, that would make this section a little less reliable. All of this can help us organize life and propose a path of descent, but depending on the data we choose to look at, again, we might get conflicting information. Consider the whale. By morphological observations, this is the most logical tree we can produce, putting whales outside the artiodactyls. But nuclear and mitochondrial DNA tell a different story, placing them inside this group. Who's right? This debate was conclusively settled by an analysis of lines and signs. And so, the whale is closely related to the hippopotamus. But you could imagine, sometimes it's not so clear-cut, and that's when we can draw from a variety of sources, morphological, molecular, internal anatomy, dental, or otherwise, to find the best agreement among the trees we construct from them. Ultimately, the more data we have, the more of this puzzle we can fill in, and, well, we've got a long way to go. But we're always getting closer.